show you how to prove the theorems I was talking about in the preceding lecture. I mean, the proofs are very difficult and use a lot of technical machinery. I mean, one could give a course on how to prove them, but it would be a very different and much harder course. This course has much less lofty goals, right? The aim of the course is to familiarize you with the objects we were talking about, so you can kind of write down their definitions and perform basic calculations with them, and see examples of what's going on. So, at the end of the day, we'll see some precise definitions, examples, and we'll just see, somehow ultimately I want you to, have some sort of, somehow I want you to get some confidence. This is really that you can actually work with these objects. I don't know if I was asked in the early stages of this game, I was asked to write some sort of preliminary somehow an explanation of what I would do in the course. I don't know, did any of you see that? Is that publicly available? I wrote some document for MSRI. And in the document, actually, one of the things I said was I might, so I'm not so sure if we're going to get there, but maybe we'll do groups other than GLN. I'm not entirely sure that's going to happen, but we'll see what happens. So there's some overall aim of where we're going, but the first thing I want to talk to you about is the local Langlands correspondence. So the first thing is going to be really part one. The classical local Langlands correspondence. So I'm going to spend some time kind of carefully defining everything that shows up in the statement of the local Langlands correspondence. So the first lecture was global, so the local Langlands correspondence for GLN over K, so here K is now a p-adic field. So very vaguely stated, so it is, vaguely speaking, some sort of canonical bijection between two sets, and I'll be a little bit vague about what these sets are. So this is certain typically infinite dimensional irreducible representations irreducible complex representations of GLN of K. That's the thing on one side. So maybe you know something about representation theory of groups. In the first course on representation theory of groups, you typically take a finite group and consider its action on finite dimensional complex vector spaces. So this is a hugely infinite group, and we have to consider certain continuous, in some sense I'll make precise, actions of this infinite group on a typically infinite dimensional complex vector space. So that's one side, and on the other side, somehow we get certain n-dimensional representations n-dimensional complex representations of a Galois group, of a group related to Gal K bar over K, the absolute Galois group of this field. So this is kind of complicated representations of a relatively simple group, I mean, in the sense that it's possible to write down elements of this group, versus relatively simple representations of a complicated group that it's quite tricky to write down general elements of. So I'm going to spend the next few lectures making precise all the terms on this side and stating the local Langlands correspondence for GLN. Before I embark on these careful definitions, I'll say if n equals 1, this turns out to be a way of dressing up local class field theory, which is the next thing I'm going to talk about. So-called local class field theory. Local class field theory has a slightly funny history. Maybe it's worth telling this story now. The main theorems of global class field theory were proved around the turn of the century before last, or whatever. Sort of the early 1900s, in some form at least, before p-adic numbers had even been invented or discovered. Then p-adic numbers and local fields were somehow, their existence was isolated and these things were studied, and people proved local class field theory by deducing it from the global results that they already had. And historically, it was only much later that people realized that actually a more natural approach is to prove the local statements first and make the global deductions from them. So that happened over a period of about 50 years, beginning of the last century. The funny story is for general N, is that this is an entirely local statement, and it is a theorem. It's a theorem of Harris and Taylor now, but the proof is global. So n equals 1, this is local class field theory. Historical remark, the first proofs of local class theory were global. So then bigger than 1. The local Langlands conjectures for GLN over K, so for K is above, K a finite extension of the p-adic numbers. The local Langlands conjecture for GLN of K are a theorem, or a 2000 theorem of Harris and Taylor, proved in Berkeley, I guess, or at least written up in Berkeley. Taylor was a Miller professor, I guess, around 2000, and he came to Berkeley with Harris, and they wrote an orange book. They wrote an orange book together. and the proofs are also global. By which I mean they use number fields. Somehow, at some stage in the proof, you have K a finite extension of QP, and you say, K must be the completion at some prime above P of some number field L over Q. And then you do things with this number field instead. And it's slightly strange because you would imagine that local assertions should have local proofs because they're simpler than global things. So now there are local proofs of local class field theory, but as far as I know, there are still really no local proofs of. In fact, in some funny sense, there's almost not a local statement of the local Langlands correspondence, because you have to say what it means for this bijection to be canonical, and that turns out to be rather trickier than one might hope. If there were somehow what the future holds. What the future holds is that this bijection should be categorified. I think that's what's happened in the function field case. Instead of being a bijection between sets, this should somehow be an equivalence of categories once you've figured out what the category should be. And I think that question is quite difficult. But my understanding is that in the function field case, well, this is something called the geometric Langlands correspondence, which has worked well in the function field case and perhaps will work in this situation soon. So now finally, let me get down to the mundane and the nitty-gritty, and let's give some details and some definitions, and let's actually do some mathematics instead of talking about overviews. So my job is to explain, precisely what everything is what everything is. So now I'll now explain everything precisely. So one thing we're going to have to learn about is Galois theory of infinite groups. So let's do infinite Galois theory then. So I do this because when I was your age, I'd been to a course on Galois theory and knew about finite Galois groups, but I didn't really know anything about. And I knew the existence of an algebraic closure, but I didn't really know anything about infinite Galois groups. So let me just start by briefly going through some stuff about infinite Galois groups. So let's just first a reminder of the finite theory of the finite case. Let's let K be any field. So K is a field. How does Galois theory, from the point of view of undergraduates, go? Let's have a finite extension. Let's say L over K is a finite extension. So of course, we say it's Galois. This is a finite extension, remember. I'm just doing a brief reminder of the finite case. We say L over K is Galois if it's normal and separable. If L over K is normal and separable. Separable is some issue that you only have to check in characteristic P. Normal just means it's a splitting field. So it's Galois if it's normal and separable, and then the fundamental theorem, then Gal L over K is the automorphisms of L fixing K pointwise, is the field automorphisms of L fixing K pointwise. And it turns out this is a finite group. I mean, that already needs some checking. This is a finite group of size equal to the dimension of L as a K vector space. And the fundamental theorem gives us a correspondence between subgroups and subfields. And there's an inclusion reversing correspondence between subgroups H living in gal L over K, these things here, biject with subfields, fields M, such that K lives in M, lives in L. There, and the correspondence is the usual thing. I guess M, if you like, M goes to phi, well, goes to G in the Galois group, such that G restricted to M is the identity. So another way of saying this, that, if you like, equals gal L over M. It's kind of a nice way of thinking about it, actually. So there's the fundamental theorem of Galois theory. As I say, at my university we teach in the finite case, and then we say rather less about the infinite case. So here's how the infinite story works. Now say let's say K is a field. And L over K is an algebraic extension. So now it's possibly infinite. Possibly infinite degree. So we have an infinite algebraic extension. So that algebraic just means every element of L satisfies some non-zero polynomial with coefficients in K, of course. So in this setting, we can still make sense. We say L over K is Galois. Same story, is Galois if it's normal and separable. These both make sense for algebraic extensions, not necessarily finite. And there's a Galois group, just as in the finite case. And there's a fundamental theorem of Galois theory, just as in the finite case, but there's a subtlety. So just let me flag the subtlety. So we set gal L over K. Same before is the field automorphisms of K. Whatever, phi from L to L, such that phi restricted to K is the identity, K to K. So it's the same definition. There's the Galois group. And of course, if you know from an undergraduate Galois theory course that if my extension is finite and the Galois group is finite and the size of the Galois group is the same as the degree of the extension, you would probably guess that in this case, if the extension is infinite, then maybe the Galois group is infinite. So actually, there is a subtlety, actually. They don't have the same size anymore, if you know about cardinalities. If this is a countably infinite extension, then you could certainly have an uncountably infinite Galois group. So in some sense, the theorem that the size of the Galois group is the degree of the extension is not true anymore if you're counting very carefully. But if you're just happy about them both being infinity, then this is fine. So there's a Galois group. So the key observation about this Galois group is that if phi is in Galois over k, then of course phi is determined by its values. Then by definition of a map, phi is determined by phi of lambda, as it were, for lambda in lambda, for lambda in L, for all. A map is no more than a list of what it does to every element. And if you think about it, if I have some random lambda in L, and if lambda is in L, then there is some finite subextension, M, L contained in M contained in K, such that M over K is finite in Galois, and lambda is in M. See, so in particular, there's a map, gal L over K, goes to gal M over K. This is just a canonical map. And phi of lambda is determined by the image of phi in gal M over K. So if I'm not interested in knowing all of phi, if I just want to know what phi of lambda is, I don't have to look in this infinite group. I just need to look in gal M over K instead, where M is, if you like, the splitting field of a min poly for lambda. That would work fine. Because if L over K is separable, then certainly M over K is separable. If L over K is normal, then M over K might not be, but if you make sure that M is a splitting field, then it will be. So let's let M be the splitting field of the min poly of lambda. So phi of lambda is determined by the image of phi in a finite Galois extension, about which we kind of know things, the fundamental theorem. In particular, phi is determined by phi restricted to M for all M. So what is this M? L lives in M, lives in K. K is our base field. L is possibly an infinite algebraic extension. M over K is a sub-extension, and this is finite in Galois. You see, every element of L is going to be contained in an M like this. So phi is determined by phi of M for all M with this property, and in particular, and gal L over K, hence injects. This is an infinite Galois group about which the Galois theory course I personally took told me nothing. But this simple argument here shows that this infinite Galois group embeds into a huge product over all M. M lives in L, lives in K, M over K, finite Galois. Gal M over K. So infinite Galois groups can be thought of explicitly as a certain subset of a product of finite Galois groups. This injection is because the function is determined by its values on every element. So there you go. This is now, of course, this is probably an infinite product if we have an infinite extension. So if you know about projective limits, you'll even see that we can do better. We can even, we've just shown that gal L over K is actually the projective limit over M as above gal M over K. But a projective limit in the category of groups, at least, a projective limit is formed as a subspace of a product, and there's the product, and there's the subspace. So this is not, this is just a reformulation in terms of fancy language about what's going on. But in particular, our infinite Galois group, which is something I'm trying to give you some kind of a feeling about, is now living in a gigantic product of finite Galois groups, and now, perhaps rather surprisingly, we get a little bit of extra structure on this infinite Galois group, namely that of we get a non-trivial topology. Now, and this is a little bit funny because gal M over K, let me, so the groups gal M over K are finite Galois groups let me give them the discrete topology. Give them all the discrete topology. If you've never seen infinite products of topological spaces, you might now make a blunder, because I want to put the product topology on this product. Put the product topology on this product over M as above gal M over K. So as I say, it's a little bit surprising at first that if you have a bunch of finite topological spaces with a very, somehow the discrete topology is every subset is open, right? So now you have some infinite product of these things, but somehow there was no topology. Every subset was open. So surely in this infinite product, every subset is still open. And that's not true. It doesn't work like that. It's quite surprising. Because the product topology isn't the first thing you would guess if you were just being very naive. If you've seen the definition of the product topology on the product of two topological spaces, so a basis of open sets, if X and Y are topological spaces, a basis for open sets on X cross Y would be U cross V, with U open in X and V open in Y. But for infinite products, it works a little bit differently. So just a reminder, the basic open sets in the product of Xi, so I is now an indexing set, and these Xi's are topological spaces. And you take an infinite product of these topological, an element of the infinite product, which is an element in each of those spaces, of course. The basic open sets in the product of Xi are of the form product of Ui, with Ui living in Xi open for all I. There's the naive guess that's not correct. And here's the truth. And Ui equals Xi for almost all I. If you know about the definition of the arrow theoretic definition of a product, then it's a good exercise to verify that this is the correct definition of a product. So in particular, even if these things are discrete, this product might not be discrete. In fact, somehow I'll tell you what we can say about it. These groups are finite, so they're certainly compact. And the product of compact spaces is compact. That's Tikhonov's theorem. So this is a compact topological space. So then this product of gal M over K becomes a topological space. And as I say, I should probably flag that it's typically not discrete. Typically not the discrete topology. And we're not really interested in this huge product. We're interested in this gal L over K, which is actually a subset. It's somehow the subset, it's the subset of elements in the product which are kind of compatible. You know when something's in gal L over K, because if you've got an element of gal M over K for every M, if these elements glue together on all overlaps, then they're going to be in gal L over K, right? And gal L over K turns out to be a closed subspace. Of this product. That's not hard. There's an exercise. You do that kind of exercise, you'll get some kind of feeling for infinite products of topological spaces. So give it the subspace topology. There we go. So now gal L over K, this infinite Galois group, is now a topological group. This is a little bit surprising if you've just seen the finite setup, because there's no topology on a finite Galois group, or none that you ever notice. It turns out that there was a topology, it was just the discrete topology, so nobody ever mentioned it. In the infinite case, the topology plays a much more serious role. And it needs to be mentioned because you can't formulate the fundamental theorem without it, basically. So the fundamental theorem of Galois theory so if L over K is algebraic, normal, and separable, is Galois, i.e. algebraic, normal, and separable, then we give gal L over K this, and we equip gal L over K with this topology, with the topology above, with the subspace topology. So, or if you're happy with projective limits of topological spaces inherit a topology, and it's that topology there. Then there's a bijection. So on the right-hand side, we have the same story. We have a L containing M containing K, some subfield. Well, on this side, it's the fields M, such that M is sandwiched between L and K. And the correspondence is between this and closed subgroups. Of gal L over K. So that's the new bit. And as I say, in the finite case, that word closed wasn't there, but it was there secretly, you see, because all the subgroups were closed, because the topology was discrete in the finite case. And if you start thinking about the infinite case, you realize that closed subgroups do play a role, because somehow, given a field M, you want to consider the automorphisms of L, which are the identity on M, and you can convince yourself that this is a closed condition. So the standard, I mean, the dictionary is still the same. M goes to the G in Galois L over K, such that G restricted to M is the identity. And one can easily check that that subgroup there is a closed subgroup. So that's where this condition comes from. So there you go. So there's the fundamental theorem. And on the way, we've seen that Galois groups get a topology. Let's do some examples. I'm really interested in local fields, but before I do local fields, I want to do finite fields. But maybe before I do finite fields, I'll just do one that we've mentioned already. Let's do somehow example 0. Let's do k is the rational numbers. Let's do somehow the union for n at least 1 of q zeta p to the n. There. I mean, let's take this union like within. We can build this in the complex numbers. So we could let zeta p to the n is e to the 2 pi I over p to the power n. So here p is prime. P is a prime number. So these are cyclotomic fields. And let's have a look at what we've got here. So a general fact about cyclotomic fields of finite degree. Why don't I say Ln is q zeta p to the n, right? So, what do we know from finite Galois theory is that Gal Ln over q is canonically isomorphic to z mod p to the n star. This is true for d roots of unity for any d. There. And so Gal L over q is now going to be some subspace or some subgroup of this infinite product, this product for n at least 1, z modulo p to the n z star. And which subgroup is it going to be? Well, again, that's pretty easy. When you see this is genuinely an injection. This is not a surjection in general. Let me show you a trivial reason why this is not a surjection. What is this map? If I've got a random field automorphism of L, then I have to give you an element of z mod p to the n z star for all n. And here's what I do. If I've got an automorphism of L, it gives me an automorphism of Ln. And so that gives me an element of z mod p to the n z star. But now, of course, if I know how this element of Gal L over Q acts on Ln, then I know how it acts on Ln minus 1, because there's this filtration, right? This isn't just L isn't just a union of all these Ln's. L is I mean, these Ln's are all, it goes like this, right? Q lives in L1, lives in L2, lives in L3, lives in Ln, lives in there. And the union of the Li is L. And so, I guess, here's what I could do. this is what I need to do. If I've got some element phi here, then I want to consider it as phi n here, for n at least 1. Phi is a random field automorphism of L, and I restrict it to Ln, and I get phi n, an automorphism of Ln, right? Phi n goes from Ln to Ln. And the thing you need to realize is, of course, if I know phi n, I of course know phi m for all m less than or equal to n, right? Because as Lm lives in Ln. So if I know what phi is doing on all of Ln, then I certainly know what phi is doing on Lm, because it's just the restriction. So if you think about it, I've just proved that this map is far from surjective. And in fact, I've told you what the image is now. If I think of phi n as an element of z mod p to the n z star, you see, in fact, somehow more, more precisely, if phi corresponds to this phi n there, and phi n is in z modulo p to the nz star, then phi m is just phi n modulo p to the m. Because that's what, what one needs to check here is that the canonical map from gal Ln over Q to gal Lm over Q, I'm identifying these Galois groups with these z mod p to the nz star, and I'm claiming that the restriction maps on the Galois side are the obvious maps on the easy modular arithmetic side. That's what this content is here. So there's some exercise that if you haven't done this kind of thing, you should maybe go and check it. And so that means that now we know what gal L over Q is now. It has to be numbers mod p to the n, which are somehow compatible if you make n smaller. So in particular, that means gal L over Q is actually not just, it really is this projective limit of z modulo p to the nz star. And if you know about the p-adic integers, then that's zp star, right? This is the units in the p-adic integers. And this is a topological isomorphism as well. So zp is the p-adic integers. Zp star has got a topology. So here zp is the limit of z mod p to the n. Z is the p-adic integers. With the usual topology. And zp star, I'm being a bit cheeky, I shouldn't really do this, but and zp star, just give it the subspace topology. That works in this particular. You've got to be careful. The issue is if R is a topological ring, then the units in R should be a topological group, but you can't always just give it the subspace topology, because in a topological group, inverse should be continuous. But as it happens, it works here. So anyway, ZP star gets the subspace topology, and this gal, so gal, this is the topology. This is the topology on gal L over Q. So there we go. So there's an example of an infinite Galois group, and we can see the topology. And the topology is something that you may be familiar with. So there's a random worked example. Now let me do some examples of things that I'm kind of more interested in, which is local fields. But before we get to local fields, let me do finite fields. let's have K finite and L an algebraic closure. Well, I mean, let's say the size of K equals Q. There. Now, it turns out that there's, up to isomorphism, there's a unique field of any prime power order, right? Then L must be somehow a union of kind of fq to the n, right? So this is a field with q to the n elements. But unfortunately, it's not like this case we had before. Here we had kind of L1 living in L2, living in L3, living in Ln, and it was kind of lovely. And I think when I was your age, I kind of hadn't thought too carefully about this, but kind of assumed that that was what the situation looked like here. So just note that we have fq, the field with q elements. That lives in fq squared, the field with q squared elements. But it doesn't go like this at all. The field with q squared elements doesn't live in the field with q cubed elements. Because if it did, of course, the field with q cubed elements would be a vector space over the field with q squared elements, and its dimension would have to be 1.5, if you think about it. If you've got a vector space over a field with q squared elements of dimension d, then it's got q to the 2d elements, right? So you see, that can't live in there for dimension reasons. So it's not as simple as this. The situation's a bit more complicated. So what's going on? So if let's use the same notation. If Ln is the field with q to the n elements, then kind of Ln lives in Lm. You see here it was if and only if n is less than or equal to m, but here is if and only if n divides n. That's how it works. And L is the union of the Ln's, if you like. It's the filtered co-limit of the Ln's, if you'd rather. So you see now, we're going to do this sort of analogous sort of story, but there's something a little bit weirder going on. So I'll remind you that, reminder, here's how the Galois theory of finite fields works. Ln is the field with q to the n elements over k. That's the field with q elements. So this is fq. And this is fq to the n. These extensions are all Galois. It's finite in Galois. Clearly, fq to the n, it's got q to the n elements, so it's an n-dimensional vector space over fq. So this Galois group's going to have order n. And one checks actually that this group of order n is in fact a cyclic group of order n. And it's not just a cyclic group of order n, it has a canonical generator. And one checks that Gal Ln over k, again, it's not isomorphic to Z mod nz. Well, it is, but I'm going to say more than that. It's actually equal to Z mod nz. There. With the generator 1 goes to Frobenius. So what is this Frob Q? Frob Q is supposed to be a completely explicit element of Gal Ln over k. So it's supposed to be an automorphism of the field Ln that leaves k fixed. So Frob Q of x is just x to the power q. And because k has q elements, Frob Q acts as the identity on k. And one checks that this is, so that, I mean, exercise, this has order n. This is the, one has to check that Frob Q is in Gal N over k, and one has to check that Frob Q's got order exactly n. And of course, once you've done that, you now know this Galois group, which had size n, must be cyclic of order n. There. And so now this, so Gal k bar over k is now going to then live in some product of z modulo nz. And now we have to kind of figure out, just as we did in the last one, we have to kind of figure out which elements are actually in this. So again, let's have G goes to Gn there. So Gn is in Z1 NZ star. So we have to figure out what the image is. So which GNs show up, which GNs glue together to give an automorphism of K bar. So the things that glue together are the things which are compatible, and what's the compatibility assertion here? So Gn is in the image. Gn is in the image of this map. If and only if the Gns are compatible, if and only if Gn modulo M equals Gm for all M dividing N. That's the compatibility assertion here. And so again, you get, and therefore, gal K bar over K is, again, using this convenient language of projective limits. It's this over N are these compatibility maps. And that's something called Z hat. Yeah. And that turns out to be the product over all primes P of ZP. So these are things, if you've never seen this kind of stuff before, you might want to go away and think about what just happened. So there's finite Galois groups. And I'm somehow a little bit reluctant to... I have 4 minutes left, so it seems a little bit ridiculous. Maybe I'll tell you what's coming up next. Oh, I finished at 15:15?
Yes.
Show me a schedule. Prove that to me. I mean, I'll quite happily speak for 90 minutes.
It sounded like 4 minutes wasn't enough time.
Oh, no. Yeah, this is great news. Okay, no, I'll happily break at 12. Yeah, okay. Yeah, let's do local fields. Great. Thank you. Local fields. So how does this work? So what is a local field? Well, I don't know. It's kind of tricky. Different people, it means different things to different people. So, for example, the real numbers and the complex numbers, maybe those are local fields. Power series rings over finite fields. I don't know too much about them, but I think those are local fields. I'm scared of them. Let's stick to the case. Let's stick to the case. K over QP finite. So here QP, this is the p-adic numbers. So this is some complete normed field, and this is a finite extension of this complete normed field. I remember when I was your age, I was quite happy with QP because I'd done all the exercises in Cassell's little book on elliptic curves. But I was always a little bit scared about finite extensions of QP. So hard luck. I'm going to do finite extensions of QP. So K over QP is finite, and the question I want to ask is what can we say about this Galois group, gal K bar over K. So any field has an algebraic closure, unique up to typically non-unique isomorphism. So choose an algebraic closure. K bar of K. And now what we want to do, we want to understand gal K bar over K. Now, somehow, in the two examples I've done so far, I did this q zeta p to the n, and I did the finite field case. In those two examples, we come out, in some sense, we worked out the answer, right? At the end of the day, we had some group that maybe we'd seen before or was related to things we'd seen before, and this was somehow an answer. So here, it's much more difficult to do that. Now, philosophically, there's a reason why one shouldn't really be able to understand this group. And that's because this group is not really well defined in some funny way. The algebraic closure k bar of k is unique up to isomorphism, but it's not unique up to unique isomorphism. So here's the problem. We have the same field k, and I choose an algebraic closure, k bar 1, and you choose an algebraic closure, k bar 2. So these are known to be isomorphic. So we can make our Galois groups. And I make my Galois group gal k bar 1 over k, and you make yours gal k bar 2 over k. And these groups are known to be isomorphic. But if we want an isomorphism, then I've got my algebraic closure k1 bar, and I look at your field k2 bar, and I have to think of an isomorphism. So I fix a random isomorphism between my k1 bar and your k2 bar. And you do just the same. You want to relate your group to mine. So you choose a random isomorphism between k2 bar and k1 bar, and the composite of those things probably isn't the identity. So as a result, we end up with two Galois groups, and we both end up with maps between them, but the composite of those maps is not the identity. It turns out to be conjugation. It turns out to be an inner automorphism. And so it's actually, somehow, if you distill this example, if you stare at this example from a great distance, you realize that in some weird way, this group is only defined up to inner automorphism, which means it might be very difficult to say anything about its elements, because the elements are somehow not well-defined things. Because somehow the elements depend on a choice of k-bar, and it's quite difficult to choose algebraic closures of abstract fields. So it's going to be less likely that we can write down explicit elements of this group. But in fact, this group is actually very difficult. So we will understand, in some sense, we'll fail. We'll fail to do this. But, we'll pick up the pieces. But we'll get some scraps. Right. So let me tell you some things that we can do to this finite extension of a QP. So, as you may well know, so recall, so QP is the p-adic numbers, right? And QP contains ZP, it's the p-adic integers. And there's this valuation. There's a valuation from QP star, well, there's a valuation from QP to Z union infinity, if you like, is the normalized valuation. So the idea is that V of x is the number of times P goes into X, as it were, the number of times. So V of kind of P to the n times a unit is n. If U is in ZP star, right, is a unit. So as I say, I was kind of happy about that when I was your age, but I was less happy about the general case of a general K. So it's all the same for general K, right? K contains OK. This is the integers of K. This is the integral closure of ZP in K, if you like. And OK contains PK. That's the maximal ideal. There, so OK is a ring, right? it's a local ring. It has a unique maximal ideal. The unique maximal ideal is pk, and this is principal. There. And a random element of k is a random non-zero element of k, at least, is a power of pi k times a unit, and there's where we get our there's where we're going to get our valuation. So there's a valuation from k star surjecting onto z. I'll normalize it in this way here. So the valuation of pi k is going to be 1. There. The valuation of pi k to the power n times a unit is going to be n if u is in OK star. That's just the units in k. So there's some valuation. So that's what local fields look like. And I personally learned a lot of this stuff. It's their local fields. So before I tell you about this Galois group, gal k bar over k, I just need to tell you a little bit more about the internal structure of k. That's what I'm doing now. Well, so now let's say L over k is an algebraic extension. So let's say L over k is an algebraic extension. So possibly infinite, if you like. If you're slightly scared about infinite extensions of p-adic fields, then honestly you can stick to the case L over k finite. So now, you see, there's going to be a valuation on L, right? So Vk extends to a map L star. The map on V was a map from K star to Z, but now I can't put Z here, right? Because, for example, if K was QP, then the valuation of P would be 1. But if L was like QP root P, if L contained the square root of P, then the valuation of the square root of P is going to have to be a half, because I want the valuation of P to be 1, and I want these things to be group homomorphisms. Vk extends to a map from L star to Q to Q. That's where I'm going to go. You see, that contains K star, and that goes on to Z. That's what's happening there. So Vk extends to a map from L star to Q, and if L over K is infinite and algebraic, it really might surject onto Q. So there's a slightly terrifying thing. Yeah, for example, if L is the field that you get by throwing in an nth root of P for all n, then you're going to get denominators. So L contains OL. It's the same story, right? L contains OL, which is just 0 union the lambda in L, such that V of lambda is greater than or equal to 0. There. And that contains PL, and that's the maximal ideal. Although in this generality, unfortunately, PL might not be principal. If we're in some complicated infinite case. But at least we have a residue field, right? So OL over PL is, let's say, KL. This is the residue field. And because L is an algebraic extension of K, so this will then be an algebraic extension of KK, which is OK over PK, which is a finite field. So you see here we have this, we have a finite field here, and then we have an algebraic extension of it. And so that'll have some Galois group, and we've seen examples of that earlier. And now by counting in the finite case, and then by some limiting argument in the general case. So all algebraic extensions of a finite field are Galois. So if L over K is Galois, then we get a map from Gal L over K to this extension of residue fields, Gal K L over KK. And by counting, one can check that this is surjective, or at least in the finite case, and then by some limiting argument. And this is surjective. But it might not be injective in general. So just while I'm erasing this, I'll maybe say an example where it's not injective. I mean, if K is the p-adic numbers QP, and then L, we just decide to throw in a square root of P. So L is QP root P. Then the integers of that, OL would be ZP root P. And the principal ideal, the maximal ideal, would be generated by root P. And the residue field would just be the field with P elements again. So QP root P over QP is going to be Galois with group of size 2. But the residue field hasn't changed at all. So the residue extension would have size 1. So this is surjective and not injective in general. So injective, obviously, equivalent to bijective. But it turns out that this map being injective or bijective is a very interesting case that needs to be studied. And in fact, it has a name. So maybe, so we say that L over K is unramified. If it's a bijection. If the natural map from Gal L over K to Gal K L over KK is an isomorphism, is injective, or equivalently bijective. So there you go. So there's some definition. So it's difficult to understand the way I've written it, I guess. So I'll just give you some equivalent ways of thinking about this. So remember, so here's the setup. We've got K over QP finite there, and K contains OK, contains PK, which is principal, let's say, generated by pi K. There. That's called a uniformizer. So the following are equivalent. So firstly is that the maximal ideal of the integers of L, the top field, is principal, and it's not just principal, but it's generated by pi K. So in the example I talked about QP and QP root P. QP, the integers are ZP, the maximal ideal is generated by P. QP root P, the integers are ZP root P, and the maximal ideal is generated by root P. So the generator changes. The following are equivalent. The generator doesn't change. L, the maximal ideal of the integers of L is principal and generated by a uniformizer in K. Secondly, do you remember I extended this valuation? This didn't get any bigger. So this, I want to call this V. Let me try and be consistent. I've called this V. Let me call this VK. I've noticed I called it VK here. So the V, the valuation I used on K, let me call it VK. So VK of L star, you see this, I'm talking about this VK here. VK of K star went to Z. VK of L star meant to maybe something that's a little bit big. K is bigger than L, right? So VK of L star might get something bigger than Z. But let's say it just goes to Z. 3 L over K unramified. There you go. So there's some exercise. So what I've done here is instead of trying to work out what this full Galois group is, I've kind of isolated a chunk of that Galois group. So I think I'll just finish by showing you what we've done here. We've certainly got nowhere near working out this full Galois group, Gal K bar over K. But we've found a piece of structure. So it turns out the composite of unramified extensions is unramified. So compositum of 2 unramified extensions of K is still unramified. So again, that's an exercise. And therefore, if L over K is algebraic, there's a maximal unramified subextension. There is a unique maximal unramified sub. There, so L lives it, whatever. L contains, let's say, M contains K. This is maximal M over K unramified. And maximal with respect to this property. And what we've done, if L over K is Galois, we're kind of interested in Gal L over K. And we haven't got enough tools to say anything about that yet. But now we know something about Gal M over K. You see. And Gal M over K is canonically isomorphic to Gal Km over Kk. You see, unramified extensions are all Galois, and this is going to be cyclic or procyclic, right? So we haven't worked out. I mean, even if L over K is Galois, we haven't said anything about Gal over K yet because we've got this big ramified extension to deal with, but at least that's something. So I'll leave it there. In the next lecture, I'm going to go on to explain everything that I know about Gal K bar over K for K a p-adic field. All the kind of group theoretic things I can say about this group. And then I'm going to tell you about tamely ramified extensions, and I'm going to state the theorems of local class field theory. That will all be tomorrow. So I'm now done until 4, and I'm going to race down the hill and pay my rent and come back. But normally I'll be around to deal with questions and have lunch with you. So I will see you again at 4. Until then, like, have some food, talk to the TAs. They're going to do something. I don't know what they're going to do. They're going to do something. And then at 4, we can have a much more informal discussion in here, perhaps. Well, we'll just see how things go. So I'll see you then. But I'm going to race off now. Sorry.